For today's video, we will be talking about elimination, specifically E2 reaction. An E2 reaction is very similar to an SN2 reaction. An E2 reaction must have a good nucleophile and it must have a good leaving group. So when we have this E2 reactions happen at a higher temperature, so that means heat will be involved. So for example, if we have this structure, okay, and this is reacting with, let's say, NaOH, and we have heat. So heat is that determines it that it is elimination for this. High temperature, OH is a very good nucleophile, and we have bromine as a very good leaving group. For an E2 reaction to happen, there's something called a beta hydrogen. Before that, this right here is a beta carbon. This is the beta hydrogen, beta carbon, and this is the beta hydrogen I circled. So beta hydrogen means, well, beta carbon means one carbon over. So let's write over here. Beta carbon equals one carbon over from the leaving group. Okay, so one carbon over from, you can say, the leaving group. So we have the leaving group here. It's connected to the alpha carbon, then the beta carbon, and then we have that beta hydrogen. So from this is a one-step mechanism. So a similar, very similar to SN2 reaction. We have the nucleophile come in. Okay. Before the nucleophile comes in, we must know that the beta hydrogen and the leaving group are on the different position. So something called anti-coplanar, right? Anti-coplanar. This means they're on opposite directions, right? So the hydrogen on the left side, we have the bromine on the right side. So these are different, these are anti-coplanar, and so E2 reaction can happen. So from this, we have the nucleophile come in, OH, hydroxide. It goes and grabs that hydrogen. This hydrogen gives off some electrons to form a double bond over here. So it goes towards the side of the bromine of the leaving group. The leaving group leaves, and so we would get a product of this, forming a double bond. Also the byproducts. It's not really important, but it's the bromine that has left, negative charge, and the water that has been formed, plus water. But our major product is the structure. And so you are going from a single bond to a double bond and elimination. So let's do another problem if we have this. And we had bromine. So E2 is that we need a good leaving group, and this was reacting with NaOH, so sodium hydroxide. So hydroxide is a very good nucleophile, OH. And let's say with this, heat, right? So heat means that E2 elimination actually in general happens at high temperature. So high temperature. Also, we have a good leaving nucleophile, but we also have a good leaving group. So this is E2 reaction. So E2 and SN2 again are similar, very similar reactions. So this is a one-step mechanism. Before we do that, we must see the beta hydrogens. So we know this is the alpha carbon, this is the beta carbon. Beta carbon meaning one carbon away. So let me write that. So beta carbon means one carbon away. So beta hydrogen means one hydrogen away. So then again, this is the beta carbon on the right side. This carbon has 3 hydrogens, but we're only going to use one of them. This carbon has 2 hydrogens, but we're going to use one of them. As you can see, they are anti-coplanar. They are in different planes. Okay, they're opposite to each other, so we can do E2 reaction. So for this, we must bring in our nucleophile. Let's start with the right side. OH will come in. It will go and grab that hydrogen, and this hydrogen will form a double bond here, where this leaving group is at, this leaving group leaves. Okay, so it's one step, but we have 3 arrows. So our first product will be like this. We have this right here, plus let's do our other product. So let's redraw the molecule. So, okay. Now, let's use this the left side. Let's use this hydrogen. So OH, the nucleophile will come. Has 3 lone pairs. One of this lone pair goes and grabs the hydrogen. This hydrogen will form a bond where the bromine is located to it. So right here. And then that leaving group leaves. So we'll get a product that will look over here. That will look like this. And so this is our 2 products that we have. Okay. So in this case, we would have 2 names for this. The first name will be that we look at it for this structure. We see that this structure has more R groups. It is more substituted where the double bond's at. As you can see, 1, 2, and 3 carbons are in the way of it. So this is the more substituted. This is called Zaitsev, meaning more substituted. And now on the other side, we have the less substituted structure. This is called Hoffman. Okay, Hoffman. One more other thing we must note is that the reagent that we've been using, this is a strong base, but also this is not bulky. So let's put not bulky. Not bulky means that the major product is the major product will be the more substituted structure. So that in this case, the Zaitsev is a major product for this case. Okay, this will change when we go forward, but for now, this is it. Now the minor product will be the less substituted according to the reagent for not being bulky. These are our 2 products that we have for this structure. So one-step mechanism must be anti-coplanar, must have heat and a strong nucleophile with a good leaving group. This is an E2 reaction. So let's bring in the same structure that we had before on the other slide. Okay, but this time let's change our reagents. This time we would have potassium terbutoxide. Again, this is with heat. We know this is elimination because of heat. A very strong base, so good nucleophile, and a very good leaving group. And so from here, we know that these beta hydrogens are anti-coplanar to the leaving group. That means E2 reaction can happen. But this time, our reagent, potassium terbutoxide, is a bulky base. And so for this, our naming of the product will be different. So let's bring in the same answers as the other slide. We had this, and then it was plus with the other structure that we had. And so now, when it's a bulky base, do we change the names? The more substituted will be called, still called Zaitsev, so Zaitsev, and the least substituted will still be called Hoffman. Okay, that's the same. But now the difference is that now the more substituted carbon will be called the minor, and the least substituted carbon will be, well, structure will be called the major. So these are our answers for this. So again, bulky groups means that the more substituted structure is the minor, and the least substituted is the major. When we had the least bulky, well, not bulky reagent, we said that the more substituted was the major, and the least substituted was the minor. Let's do another example. This time let's have the bleeding group on a wedge. We have it on cyclohexane. This is reacting with, let's say, sodium hydroxide, and under heat. So heat is elimination. We have a good nucleophile. We have a good leaving group. Let's see if the beta hydrogen are anticoplanar. So we have a wedge. That means the beta hydrogen should have a dash. So on here, let's say the beta carbon, 1 carbon away, would be here and here. So looking from this carbon over here, we see that one of his hydrogens, we can give it a dash. So that means this is anti-coplanar, and E2 can happen in this stage over here. Let's see the other carbon. This other carbon, we could just say that this hydrogen over here has a dash. It does have a dash. So dash and wedge means that they are anti-coplanar. So that means that we'll get two products for this. So let's start with the bottom one. The bottom portion, the OH would come. OH, negative charge. One of the lone pair goes and grabs that hydrogen. This hydrogen gives off the electrons to form a bond here. Now the leaving group leaves, gets kicked out. So our first product would be this. Okay, so methyl group, leaving group's gone, and we have a double bond here. And with our second product, let's redraw the structure of our original problem. So the hydrogen here, the OH will come, negatively charged, and go and grab that hydrogen. This hydrogen gives off some electrons to form a double bond here, kicks off the leaving group. Okay, as you notice, the hydrogen goes towards where the leaving group is. It does not form a bond here. Okay, the leaving group is nowhere on this side, so it goes on the side where the leaving group is at, which will be this side for this in this case. And you can't jump over. It cannot do this, or it can't do this. It can only go that carbon between the bromine and the beta hydrogen. So from this, we would have a reaction. Our product over here. Oops. Okay. This. So in this case, we have to notice which one is Zaitsev and which one is Hoffman. As you can see, where this double bond's at, it's on this carbon and on this carbon. So these two carbons are connected to 1 and 2 carbons. So this is a secondary carbon. Okay, secondary on this double bond. For this one, we see that the double bonds here and here, it is connected to 1, 2, and 3 carbons. So this is tertiary for it. The more the carbons, the more it is stable, which is more R groups, meaning more substituted, which in this case, this is the Zaitsev. And this means this is the Hoffman, less substituted. Okay, and then for this case, let's see. We see that the reagent is not bulky. So when it's not bulky, that means that the major will be the Zaitsev, not bulky. So in this case, the major is the Zaitsev, which the minor is the Hoffman. And so these are two products for this answer. So let's say we have this structure. As you can see, we have heat, high temperature, that's E elimination. We have a good nucleophile, and then we have a good leaving group. So this can be E2, but let's see the beta carbons. So the beta carbons are here. Okay. Let's see the beta hydrogen for this. This means they have to be anti-coplanar. We have 3 hydrogens here on this carbon, but we're only going to use one of them. So let's go back. Here we have an anti-coplanar, right, on this carbon. So this can happen in E2 reaction. So we have the nucleophile coming in. It has a negative charge. One of the hydrogens, the lone pair from the oxygen goes and grabs that hydrogen. This hydrogen gives off some electrons to form a double bond on the side of the leaving group, which is here. The leaving group leaves, and so we would get our first product. Okay, this dash means there's a methyl group here, and so we would have a structure that would look like this. Draw right. And so from this, we would see it having a Hoffman name for this. This is because this will be the less substituted. Okay. As a matter of fact, we'll do that for the end. But this is one of our product, and let's see if we have another product. On the second beta carbon, we see that the beta hydrogen has a wedge in this case because the methyl group has the dash. So we have the leaving group on a wedge, the beta hydrogen on a wedge. They are on the same plane, right? They're on the same side. So we call this syncoplanar. But for an E2 reaction to happen, we must have an anticoplanar. So this cannot work on the right side. But we see that this is a long chain, right? A straight chain. This is a pentane. This is not a ring. So something can happen here, something called a Newman projection. So we could do a Newman projection to actually change it, the beta hydrogen, to put it on an anticoplanar plane. So in this case, if I was looking here on this side, we would draw the Newman projection for this. Up top, we see that this group right here, right? So a methyl group, like that. Well, bring it, and then go to the methyl group, an ethyl group, okay? Now, for Newman projection, this is a trick. A wedge means on the right side, and the dash means it is on the left side. The dash is left. So in this case, we have the hydrogen on the wedge. Wedge means right, and so the hydrogen would go here. We have the methyl group on the dash, so dash means left, so we would have it like this. Let's put CH3. Okay. Now for the back carbon, we see that there's a bromine on the wedge. That means right side, so we'll put that on the top. Br on the left side, we have a dash, right? We have a hydrogen on a dash, that means left. So the hydrogen would go here, and so we would have the methyl group on the bottom, like this. In this case, we see that the leaving group is here, the beta hydrogen is here, they're on the same plane, right? So let's switch it. Let's actually move the front carb. Actually, let's move the. For this, we can either move the back or the front carbon. So from here, let's move the front carbon, and so we're gonna move it maybe three times or twice, to get it on the same different anticoplanar position. And so we would leave the back the same. Okay. And so we want the hydrogen to be here. So the hydrogen's here. The CH3 is here, and then we have the ethyl group here. So now we see that the bromine, the leaving group, and the beta hydrogen is on anticoplanar. They're on opposite sides. This means E2 reaction can happen. We bring the leaving group, actually the nucleophile, right? Nucleophile comes, it grabs the hydrogen, this forms a bond here, the leaving group leaves. This will give us a reaction that would look like this. CH3, CH3. Okay, we have the hydrogen here, and we have the methyl group here. So the beta hydrogen and the leaving group is gone. So now we can draw the structure. For this, let's draw it up here. So on the, let's say on the right side, it doesn't matter where we put it, but on the right side, we have the methyl group. The methyl group is up. So before we do that, let's draw the double bond, because we formed a double bond here. So the methyl group is up on top. That means it will be up on top. CH3. And the bottom of it right here is the ethyl. So like this. It's on the bottom, so it goes on the bottom. On the right side, on the left side, we have the hydrogen on top. You don't have to show it, but I'm just going to show it. It's on top on the left. And then on the bottom, we have the methyl group, like this. And so these two are our structures, our two structures, the two products for this. This is the Hoffman. It's less substituted, because it's, according to this, we have the two carbons is only connected to one carbon over here. Let's see, one carbon over here, and so this makes it primary. But this carbon over here, these two carbons are connected to, let's see, 1, 2, and 3 carbons, makes it tertiary. So this is the Zaitsev, and we see the reagent is not bulky, and so that means the major is the Zaitsev, and the minor is the Hoffman, and there are two products for this. So going back to our answer from the other slide, we had this, and we said this was the minor, and we had our other product that would look like this. Have the double bond here, the CH3, right, the methyl group, and then had the ethyl, and had the other methyl, right, and I had the hydrogen here, which you don't have to draw, but I did. For this, we can actually see something. Just be aware that we can actually put the E and Z formation for this, the notation. So in this case, we see that the bulky group, when comparing this side's more heavier than the hydrogen, and the ethyl is bigger than the methyl. So this is a Z notation. So just be aware of that. E and Z notation can take place in this if a professor does ask you for it. So moving on for our different structure for this, if we had a phenol group here, and we have the leaving group here, we had a wedge here. So this is a methyl group. Now let's see the beta carbons for this. Before we do, let's react this with NaOH. So NaOH. From here, we have the heat. We can do this heat, good nucleophile, and a good leaving group. The beta carbons are here, one carbon away, and here. So this carbon over here, it can't do anticoplanar because there is no beta hydrogen, right? So there's no beta hydrogen here. That means the right side, this side cannot do anticoplanar. So yes, that is it. For the left side, you see that the hydrogen has a dash. So the leaving group has the dash. The beta hydrogen has a dash. Dash dash means same plane. That means anticoplanar cannot take place. But we see that there's a chain here, okay, on the chain, and we can do the Newman projection as last time, and we can rotate it to form a anticoplanar. So we only have one anticoplanar beta hydrogen here, so that means we will have one product only one product, okay, because the right side cannot do E2 reaction. There is no beta hydrogen, okay. On the left side, there is a beta hydrogen, and we will do Newman projection to make it anticoplanar. So from here, if I was looking from this side, okay, first thing we want to do is look behind it over here, and this will give us the phenol, right? So I'm just going to put pH, but just be aware I'm talking about this cyclohexane, right? So this is on top. Next comes the carbon that is attached with the hydrogen. The hydrogen has a dash, and we said dash means left, so we put here, left side on the bottom. Next we have the methyl group, has a wedge, that means right side. Now we look on this carbon over here, we have the bromine on the wedge, so that means it is on the left side. How do I know it's top? Because on the top side you can do two, right? On the bottom you can only do one, so we have put it on the top side on the left because it is a dash. Dash on Newman projection will mean up, left. Now we have a wedge on this hydrogen, this means right, and then we have a tert-butyl on the bottom. The leaving group's here, the beta hydrogen's here, they're on the same plane. Let's switch it, rotate it, so they can be on the opposite. So this will take place, that's too big, but this will take place. Let's rotate the back carbon, so let's keep the front the same. It doesn't matter what you rotate, but they just got to be anticoplanar to each other. So now the bromine's here, the hydrogens here, and we have the tert butyl here. So I switched them twice, rotated twice, okay? Now we bring in the nucleophile. Hydroxide comes in, grabs the beta hydrogen, forms a double bond here, kicks off the leaving group, giving us a product that would look like this. Still got this methyl group here, the hydrogens here, and the tert butyl here. So the beta hydrogen and the leaving group is gone. Let's bring our reactant here. So let's do this. We form a double bond, we know that. It doesn't matter where you put it, left or right, but I'm just gonna put it on the right side for this, the front carbon, right? So on the front we have the phenol, right? Oops, that's too big. Let's put it over here. I'm gonna change it up. Okay, there you go. And on the bottom we have the methyl, right? The methyl, like this. On the top we have the tert butyl on the left side. Okay. Doesn't matter if you put it left or right, but just know it goes on the top, because you can see it's on the top here. It's on the top. And the bottom, at the bottom we have the hydrogen, so that means the bottom, well, the hydrogen will go. You don't have to draw the hydrogen, but I'm just going to show you. So this is the Zaitsev, because it'll be more substituted than if we had the Hoffman. Okay, this is the major product, so let's write that. Before we do that, we can do E and Z formation. On the left side, we see that the tert butyl is stronger and the phenol is stronger than the methyl, and so this is a Z formation. This is also the Zaitsev problem, and this is the major product. There's no minor product, just major. Only one product, and this is the answer for this problem. Okay, now what if we have the structure and we had a methyl group, and this was reacting with, let's say, NaOH, ethanol, and this is with heat. And heat, and so we have heat, a good nucleophile, and a good leaving group. In this case, let's see the beta carbons, right? The beta hydrogens. So the beta carbon is here and here. On the left side, we have two beta carbons, two beta hydrogens. Let's put one on a dash, right? For this, it is anti-coplanar because this is a dash, and we have a wedge over here, so different plane. So E2 can happen here. So let's bring the nucleophile, okay? Okay, negative charge. It goes and grabs the hydrogen. This hydrogen forms the double bond towards the leaving group side here. The leaving group leaves. And so our first product would be this, with the methanol over here. Now let's redraw the original problem and see if we could do it on the right side. So we have the beta carbon over here, and we have the hydrogen over here on a wedge. So the wedge and wedge, they both have a wedge. That means they're on the same plane. This is actually called syncoplanars. And so this needs to be anti-coplanar for it to work. So we said before we can do Newman projection to see, to rotate it and make it anti-coplanar like our last two examples. But this is a cyclohexane. Cyclohexane cannot be put into Newman projection. So no Newman projection, right? If it does go in Newman projection, it can't rotate. If it does rotate, it will break, okay? So again, if you put this in a Newman projection, it will not be able to rotate because it can't rotate, and if it does rotate, it will break the ring. And so rings, cyclohexane, cyclopentane, they can't do Newman projection. So in this case, they will have, this product will be only one product. We'll have one product for this, because on the left side can do it, can do the E2 reaction. This will be the Hoffman name for it. The reagent is not bulky, and so this will be the minor product for it. Okay, the reason for this is Hoffman. It is less substituted. Okay, so we see that there's only connected to 1 and 2 carbons. The Zaitsev would have been connected to 3 carbons, making it more substituted. This is why this is Hoffman. So let's do another example here. We have a cyclohexane. And so this we would have a wedge. Let's put a wedge here. Let's put a tert-butyl. Okay, let's put another wedge here. And put this leaving group here. And a methyl. Okay, so it can't do a Newman projection, right? Well, we could do something else. Cyclohexanes can form a chair conformation. So chair conformation, let's number it. We have 1, 2, 3, and 4. On the first carbon, we have a wedge. Wedge means up. And on this carbon over here, we have numbered. It is an up position, so that means axial, up, up. So our tert-butyl goes here. On number 2, the second carbon, we have a wedge. That means up, but this is a downward position, so it goes on the equatorial side. On the fourth carbon, we have a dash. That means down. And on the fourth position, it is a down position. Down, down means axial position. So methyl group here goes here. For a reaction to happen, let's say NaOH in heat, right? For this to happen, we must have the leaving group and the beta hydrogens on the axial position. So the beta carbons are here, okay, and the beta hydrogen for this will be here, right? This doesn't matter on the third carbon because they're both hydrogens. Okay, that doesn't matter, but we must have this this beta hydrogen on the axial position and also this leaving group on the axial position. So we do a ring flip. Okay, let's just renumber it 1, 2, 3, and 4. So from here, on number 1, we had a wedge, right? But it's downward position here. It goes on the equatorial side. Okay, the bulky group. The tert-butyl is the most bulkiest group, and so when you have bulky group on the equatorial side, it is more stable. Okay, this makes it more stable. That is good. That is what we want. On the second carbon, we have a wedge. That means up, and we have up position here, so it goes on the axial position, which will be here. Oops, straight up. Here, and then on the third position, third carbon, actually we have nothing. It's just a hydrogen, so we have the beta hydrogen on the axial position, which is good. This one right here, particularly. For the fourth carbon, we have a dash, that means down, but we have a up position here. It'll go on the equatorial side. Change this. Okay, for this we have the leaving group on the axial position. We have the beta hydrogens, right, on the axial position. This beta hydrogen over here is on the axial position, so that means an E2 reaction can happen. So let's say we bring in on the E2 reaction can happen here, actually. And so this is the better product to have. Not the better product, but the better chair position to have than this position.